This is video number 6 on the topic motion in a straight line and second on differentiation. Timestamps are given in the description box. You can watch parts of video if you are running short of time. In this video, I'll discuss finding derivatives of simple function from first principles and some properties of differentiation, how to find derivatives of complex functions using properties of differentiation, and the results of derivatives of simple functions. I'll discuss some 5 examples where derivatives is found out from the first principle and using properties of differentiation. I'll discuss a practical example for moving car. Finally, I'll summarize this video. Finding derivatives from first principle. This is the first example. We have a function y equal to f of x equal to x square. So this function is the mapping between x and x square. So to find the derivative of this function from first principles. So the definition of derivative is delta y by delta x in the limit delta x tending to 0. This is called dy by dx. And delta y is a change in the function value when x changes from x to x plus delta x. So delta y is f of x plus delta x minus f of x by delta x in the limit delta x tending to 0. So in this example, the function is x square. So this will become x plus delta x whole square minus x square divided by delta x, and then the limit has to be put. This can be simplified. This a plus b whole square, so will be a square, this will cancel, and the cross term 2x delta x plus second term square divided by delta x, and the limit has to be put. So since delta x is not 0 but it's tending to 0, delta x can be cancelled. We cannot cancel 0, but we can cancel a quantity which is very close to 0, tending to 0. So delta x is tending to 0, so delta x can be cancelled, and then you have to put the limit as delta x tends to 0. So this term will go, so we'll get the answer as 2x. So derivative of x square is 2x. So this one is explained here. By definition, dy by dx, that's derivative of the function y, is limit delta x tending to 0 of delta y by delta x. And delta y is nothing but change the function value when x changes by an amount delta x. Here the function is x square, so it will be x plus delta x whole square minus x square by delta x. So this a plus b whole square, and this divided by delta x, so 1 delta x will cancel. So in the limit it will be 2x. This is the second example, finding the derivative of the function x raised to the power n. So again, by the definition of the derivative, the function is x raised to the power n. So by definition of the derivative, dy by dx is delta y by delta x in the limit delta x tending to 0. So this will become x plus delta x raised to the power n. That is the value of the function y at x plus delta x minus the value of the function at x, that's x raised to the power n, divided by delta x, and we have to put a limit. So to solve this, we use a algebraic identity. A raised to the power n minus b raised to the power n is a minus b into a raised to the power n minus 1 plus a raised to the power n minus 2 into b plus so on plus b raised to the power n minus 1. The way to remember this is it's a polynomial in nth degree. So here one degree has come out. So the remaining should be n minus 1 degree. So this will be a raised to the power n minus 1, b raised to the power 0, and the power of a will go down and the power of b will increase. B raised to the power 0, b next to b square b cube. Finally, will be raised to the power n minus 1. So any term is of the order of n minus 1. So this is easy to check. This will be this term, and this minus into this thing will be the second term, and the remaining terms will cancel. So using that identity, we can solve this one. So a minus b is delta x into a raised to the power n minus 1 plus a raised to the power n minus 2, and then this b will start appearing plus last term will be x raised to the power n minus 1 divided by delta x, which will get cancelled. So in this you have to put the limit as delta x tends to 0. So here there are n minus 1 terms because, sorry, n terms. B raised to the power 0, 1 up to n minus 1. So it is 0, 1 up to n minus 1, n terms. So in this we put delta x equal to 0. Each term will be x raised to the power n minus 1. This first term is x raised to the power n minus 1. Here delta x is put to 0. This is x raised to the power n minus 2 into x raised to the power 1. It's x raised to the power n minus 1. So all the terms of x raised to the power n minus 1 and we get n times x raised to the power n minus 1. So we get the result derivative of function x to the n minus 1 is n into x to the n minus 1. So n is coming down and the power is going down by 1. So this we have derived the derivative of the function x to the n from the first principles. So this what is done here. By definition, derivative is delta y by delta x in the limit delta x equal to 0. Delta y change the function value when x changes by x plus delta x. So here f of x is x raised to the power n. So it will be x raised to the power n, x plus delta x raised to the power n minus x raised to the power n by delta x. So this is a raised to the power n minus b raised to the power n form. So it uses algebraic identity, this one. So a minus b is, this one is just delta x, and then a raised to the power n minus 1 is the first one, raised to the power n minus 1. And then second term is a raised to the power n minus 2, so this raised to the power n minus 2, and then b, which is x. Third term is this power will go down, and this power will increase. And the last term is x raised to the power n minus 1. So here, divided by delta x, so since delta x tending to 0, not equal to 0, this delta x and this delta x can be cancelled. And there are n terms here because here the x raised to the power 0, x raised to the power 1, 2 up to n minus 1. So 0, 1, 2 up to n minus 1, it's n terms. So n terms, and the value of the term is when you put the limit delta x to be 0 is x raised to the power n minus 1. Here will get x by n minus 2 into x. So x raised to the power n minus 1. Here x raised to the power n minus 3 plus 2. So it will become n minus 1. So we'll get x to the power n minus 1 n times. So this is the result we have. Derivative of x to the power n is n times x raised to the power n minus 1. So when you differentiate, the power goes down by 1. Third example of finding derivative from the first principles. The function is sin x. So again, using the definition of the derivative, which is dy by dx equal to delta y by delta x in the limit delta x equal to 0. And delta y is change the function value when x changes by delta x. Sin x. So dy by dx by definition is delta y by delta x, and the limit delta x tending to 0. And delta y is the change the value of function y when x changes from x plus delta x to x. So this is sin minus sin x by delta x, and then the limit has to be put limit delta x tending to 0. So for solving this, we'll use a trigonometric identity sin c minus sin d equal to 2 cos sin, and this is angle is c plus b by 2, and this angle is c minus d by 2. So if you do that, 2 cos this plus this by 2 is x plus delta x by 2, because x plus x is 2x by 2 is x, and then delta x by 2, and then sine difference, so it's delta x by 2 by delta x, and you have to put the limit. So this 2 can be brought down here, and I lose the result sine delta by delta in the limit delta tending to 0 is 1. So that's the standard result. So here delta is this. So this quantity is sine delta by delta is delta x by 2. So this thing tends to 1. And here if you put delta x tending to 0, I'll get the answer as cos x. So derivative of sin x is cos x. So this is what I done here. So delta y is sin x plus delta x minus sin x by delta x. So sin c minus sin d formula, which is 2 cos sin, and the angles are c plus d by 2 and c minus d by 2. This result comes from sin a plus b formula, which is sin cos plus cos sin. It's sin a cos b plus cos a sin b, and sin a minus b is sin cos minus cos sin, sin a cos b, and then cos a sin b. So a plus b is put as c, and then a minus b is d. So if you subtract these two, the first term will vanish and the second term will get added up. It will be 2 cos sin. That's what is here. So this is a basic trigonometric identity we should remember. So using this, I'll write 2 cos sin, and the angles are this plus this by 2, and then this minus this by 2. And this delta x, these two can be brought in here. So this quantity is of the form sin delta by delta in the limit delta tending to 0. Here delta is delta x by 2. As delta x tends to 0, delta x by 2 also tends to 0. So this quantity is 1. Here if you put delta x to 0, it will become cos x. So this again finding the derivative from the first principles. Next example is cos x. It's similar. By definition of derivative is delta y by delta x in the limit delta x tending to 0. And delta y is change the function value when x changes to x plus delta x from the original value is f of x by delta x. Here the function is cos, so it's cos of x plus delta x minus cos x by delta x. Here we have to use cos c minus cos d formula. Cos c minus cos d is minus 2 sin sin, and the angles are c plus d by 2 and c minus d by 2. So this is got from this identity. Cos a plus b is cos cos minus sin sin. This you should know. And then cos a minus b is cos cos plus sin sin. So from this, a plus b is put as c and a minus b as d. So this is a change of variables where a and b is changed to c and d, and the relation between a, b and c and d is a plus b is put as c and a minus b is put as d. So if you subtract these two, I'll get this one, where the first term will cancel and the second term will become minus 2 sin sin, and the angles will be c plus d by 2 and c minus d by 2. So using that, cos minus cos will become 2 minus 2 sin sin, that is sum of the angles by 2, and then difference of the angles by 2, or c minus d by 2. So here Again, this 2 can be brought down here. Again, you have this form sin delta by delta. This is 1. And here, if you put delta x equal to 0, I'll get minus sin x. The minus sign is here, which comes from here, and which comes from here. So derivative of cos x is minus sin x. Some properties of this derivative operator. The first property is derivative of function c into u is c times derivative of the function u. U is a function of x. So for example, I know that the derivative of the function, for example, let me consider this function u is x squared. I know derivative of du by dx as 2x, which is derived earlier. And suppose I want to find derivative of the new function d by dx of 5 times x squared. We just have to get this as 5 times derivative of d by dx of x squared. So 5 times the constant will come out. So if you know this thing, you don't have to do the derivative again. So this is just 5 into 2x. So it is 10x. So using this property, we can get the derivative of the function 5 times x squared. Next property is we have two functions of x, u and v. We know the derivatives of u and v individually. Like I know du by dx and dv by dx. From that, can I find out the derivative of the function u into v? So the rule is u into derivative of the function v with respect to x, and then v into derivative of the function u with respect to x. So if I know du by dx and dv by dx, from that I can find the derivative function d uv by dx. So this rule can be checked for a simple example. I'll take x as u as x and then v also as x and see whether this is true. So the right hand side is u times dv, so dv by dx is dx by dx, which is 1, plus v times du by dx is again 1 divided by, that's all. So this is 2x. And this is d by dx of x square, which is 2x. So this is true. For this simple example, this is just to get the feeling that the rule is correct. Next is the quotient rule. We have two functions which are getting divided. So I know the individual derivatives of u and v. So can I find the derivative of u by v? So it's v into derivative of u minus u into derivative of v divided by v square. So this also can be checked for a simple example where we'll take u as x square and then v as x. So the left hand side is derivative of x, which is 1. So the right hand should also give me 1. That we can check. V is x and then derivative of u is 2x minus u is x square and the derivative of v, which is x, is 1 divided by v square, which is x square. So it is 2x square minus x square by x square, which is 1. So this rule is checked for this simple example. So we get the feeling that this rule is correct. So this rule is also called UV rule and U by V rule. Next example of finding the derivative of the function y equal to tan x. So this one, instead of finding the derivative from the first principles, we can use the property of derivative, that's U by V rule. Tan x can be written as sin x by cos x. Tan is sin by cos. Okay, and then we can use this UV rule. UV rule says it's V into du by dx. V into du by dx and then u, which is sine, and the derivative of v, which is minus sine x. Derivative of cos is minus sine, divided by v square, which is cos square. So this is cos square plus sine square, which is 1. Basic trigonometric identity. Sine square plus cos square is 1, divided by cos square, and 1 by cos square is secant square. So we get the result that derivative of tan square is tan x is secant square. So from the first principles and using the properties of derivatives, we can get derivatives from some standard functions. Derivative of sin x is cos x. This can be derived from the first principles. Derivative of cos is minus sine. This also can be derived from the first principles. Derivative of log x to the natural logarithm base e is 1 by x. This also can be derived. And derivative of e raised to power x is e raised to power x. The function which is not changing when the derivative is taken is unique function, which is e raised to power x, exponential function. Even these two can be derived from the first principles. Derivative of tan x is secant square. This can be derived from u by v rule. Tan can be written as sine by cos. Similarly, cot is minus cosecant square. Cot can be written as cos by sine, or it can also be written as 1 by tan. Again, using u by v rule, we can get this one. Derivative of secant x is derivative of 1 by cos. Using u by v rule, we can get this one. And derivative of cosecant x is minus cosecant as cot x. Cosecant x is 1 by sin x. So again, I can use u by v rule, where u is 1 and then v is sin x. So these are some standard results which we should remember. One interesting thing to note is the derivative of sine is cos, but the derivative of cos is minus sine. So how to remember this sign? One way to remember is in the first quadrant, some sine function. First quadrant means from 0 to 90 degrees. Sine will go like this. This is sine function. And then cos 0 is 1. So this is cos. And the derivative has the interpretation, it's a slope of the curve. So sin x slope is maximum here and then it becomes 0. So that is matching with cos x. So derivative of sin x, which is the slope of sin x curve, is matching with cos x. So with the plus sign. But if we take the cos curve, here the derivative is 0 because it's maximum point. After the derivative is negative because it's going down. And here the derivative is maximum negative. So it is not matching with sin x, but it will match with minus sin x. Suppose if you plot minus sin x in this same graph, minus sin x will look like this. Just multiply this by minus 1. So this is minus sin. So derivative of cos is negative, it's matching with minus sin. So that's why this minus sin is there here. Or you can simply remember, this is slope and derivative of sine. Slope of the sine curve sine is positive. That's why the positive sign is here. And derivative of the cos curve is negative. That's why it's negative sign is there. That's another way to remember this sign. So this is a practical example where x is shown as a function of time. So here the two variables are t and x. So car is moving on a straight line from initial location, say x equal to 0, to some location around 280 meters in 20 seconds. So this is the trajectory of the moving car starting from here at 0 seconds. It moves and reaches 280 meters at 20 seconds. And it's going straight, there is no turning back on that. Because x is constantly increasing. What is setting means x will decrease, but x is monotonous function, it's increasing. So here you can see x is increasing like a curve. After this part is straight line. After this also a curve, and after this flat. X is not increasing. So here the thing is at rest. So here the car stops moving. That's why the x is constant after this time. So this part of the curve is like a U, and this part of the curve is like an inverted U. So the difference between U and inverted U is the slope, how it is changing with time. So in this curve, the slope is like this, and then slope becomes steeper, and here it is steepest. So the slope is increasing. There's the property of the U curve. This inverted U curve, here slope is got some value, here slope is decreasing, and at this point slope is minimum or it can be 0. So here slope is decreasing. And for a straight line, the property is slope equal to constant. So given this xt curve, we can find the Vt curve using the relation the velocity is dx by dt, which is slope of xt curve. This is the geometric interpretation of the derivative. So here the slope is decreasing, slope is constant, and slope is decreasing here. So the velocity time graph of this motion will look like this. So velocity is increasing because the slope is increasing, and then the velocity is constant because slope is constant. After that, the velocity is decreasing because slope is decreasing. So here the slope is 0 because it's a maximum point. It's a maximum point, and here it's a minimum point. So this is u. This is the bottommost point, so the slope is 0. That is inverted u. At the topmost point, the slope is 0. So here the velocity is 0, there also the velocity is 0 because the slope is 0. And here the velocity is constant because the slope of a straight line is constant. So the pink highlighted region corresponds to the straight line part where the velocity is constant. So we got this Vt curve from xt curve using the geometric interpretation of derivative that it is the slope of the curve. Velocity is dx by dt, the slope of xt curve. So given Vt curve, I can find acceleration of this motion using the relation that acceleration is dv by dt. Geometrical interpretation is slope of Vt curve. So here we have Vt curve. So this is also like u. Here the slope is something. Here the slope is maximum steep. Here in between value. So here also the slope is increasing. And here horizontal line the slope is 0. The line that's going up, the slope is positive. Going down is negative. Horizontal line, the slope is 0. So here the slope is 0. Here slope is negative. And it's constant because it's constant slope. And also constant. Here it's increasing slope. So the acceleration of this motion will look like this. The first part, acceleration is positive and it's increasing. Second part, the acceleration is 0. The third part, constant acceleration, but it's negative value because the slope is going down. Velocity is going down, the slope is negative. So acceleration is negative. Here the acceleration is positive and it's increasing. Here the acceleration is 0. So first part of the motion, the acceleration is increasing. After that, constant velocity, so acceleration is 0. After that, the vehicle is stopping, so acceleration is negative. So this is a practical example where we can find velocity acceleration using the geometric interpretation of derivative. To summarize, derivative from first principle is found using this one. Derivative dy dx is nothing but delta y by delta x in the limit delta x tending to 0, and delta y is change the function value when x changes to x plus delta x from the original value x divided by delta x. So this can be manipulated for the given function, and we can get the derivative of functions from the first principle. And this derivative operator has got some properties. If you know derivative function u, derivative of function c times u, where c is a number or a constant, you just have to take the c outside. So it will be c times the derivative of function u. Similarly, if you know derivatives of function u and v, I can find the derivative of product u into v. For example, if I know derivative of function x and sin x. From that, I can find the derivative of x sin x using this right hand side. And then quotient rule, derivative of v by u or u by v is v into du by dx minus u into du by dx by v square. Denominator is still in here, and then first put v and then derivative of u, and then minus sign because u by v equal u into du by dx. Derivatives of standard functions which we have to remember. This we can derive by first principles, but after that we have to remember this result. Derivative of sin is cos, and there is a plus sign here because Slope of the sine curve in the first quadrant is positive. Derivative of cos is minus sine. Minus sine we can remember as the slope of the cos x curve in the first quadrant is negative. Derivative of log is 1 by x with a natural logarithm base e. And then derivative of e raised to power x is e raised to power x. The function whose derivative is same as the function is this unique function, exponential function. Derivative of tan is secant square. Derivative of cot is minus cosecant square. Derivative of secant x is secant x tan x. And derivative of cosecant is minus cosecant x cot x. You can ask your doubts in the comment section.